Hello, today we're going to explain the topic of inflection points and intervals of concavity. As you know, we're going to find our inflection point, we need to find the second derivative of the original function. But first, we must state that the first derivative, its point is to find either if the line increases or decreases. The point of the second derivative is to find if the critical value is concave upwards or concave downwards. So it's minimum or it's maximum. So first we find the first derivative, which is 3 squared minus 6x minus 9. And then we need to find the second derivative, which is 6x minus 6. Then we need to find x. So our inflection point will be x equals 1.
This point is the x of the inflection point. And with it, we're gonna find the intervals of the concavity, which is gonna tell us if it's concave up or if it is concave down. Here we have this interval, which is minus infinite to 1, and this interval, which is 1 to infinite. We choose a number between the interval, and we choose 0 here, and we substitute in the second derivative. 0 plus 6 is 0, minus 6 is minus 6. And here we choose the 2, which is a number between 1 and infinite. 2 plus 6, 12, minus 6, 6. This 6 is negative, so it means that the concavity is down. This 6 is positive, which tells us that the concavity is upwards. This is going to be like this, and this is going to be like this.
To get the y of the inflection point, we'll have to replace the x value of the second derivative into the original function. Here is the result. We have negative 11, so the inflection point is 1, negative 11. So here in the graph, this is the original graph, so we'll have to mark the point of inflection. It is more or less at this point. So here it is, the point of inflection of our function.
To analyze a function using derivatives, we need to take the derivative of a function, and from that derivative we can take the critical points. The critical points are also the local points or extreme points in the function, the x points. To get the y point, you need to substitute the critical value in the original function. To see if it's increasing or decreasing, you need to replace a close value to the critical point in derivative, and if it's a positive number, the function is increasing. As in if a negative, it is decreasing. And with the second derivative, you can find the concavity of the function. The point which equals to 0 is an inflection point. The inflection point is the point in which the function is starting to change. As the same in the first derivative, to find the concavity of this function, you need to replace with a number that is lower than the critical point or bigger than the critical point.
Based on the results from the first derivative, we see that the graph first increases, then decreases, and finally increases to infinity. We select the local maximum and minimum points based on the extreme points. Then we select the point of inflection to determine where the graph starts to be concave down and concave up.
Okay, now we're going to see the related rates of change. for example, here we have this word problem. It tells us that a stone is thrown into a lake and it forms a circular waves, and we need to find the speed at which the area of the waves is changing when the radius is equal to 5 feet, if at the time the radius is increasing at a rate of 1 feet per second. So first we have to take our numbers out from the word problem here, from the sentence, and we plot them here. We have a radius of 5 feet, a rate of change of the radius of 1 feet per second, and they're telling us to find the area from the circular waves, at which rate they are changing the area. So we need to find this. So what we do is we get the area of a circle, because they are telling us there is a circular wave. So we first get the derivative of the area of the circle with respect to time. Once we get it with respect to time, we can see that we have derivative of area with the respect of time, and then 2 times pi. We remove the 2 to form an r for radius, and we also have to plot the point. Once we derivated we find the derivative of radius, the radius in respect to time. Once we have this equation, we replace the points needed with the variables that we got here before. So we know that radius is equal to 5 feet, and the rate of change of radius in respect to time is 1 feet per second. So 2 pi times 5 is 10 pi, times 1 is 10 pi. So the area changes with respect to time of 10 pi feet squared by second.